So I work on something called the Dark Energy Survey, which is basically making a map of the distribution of galaxies on the sky, and then inferring how the universe has evolved based on the characteristics of the distribution of the galaxies in this map. In other words, how they're clumped. So if it was just a uniform distribution of these fuzzy things out there, we would conclude that there is no structure. But they are clumped, and therefore there is structure. And one of the things that scientists like to do is try to account for not just what is it, but how did it come to be? In other words, the origin of how the structure evolved. And so that's really the game. So to be a little more concrete about it, the physical framework that we are using, which is not to say that it's correct, but it's the one that we find useful, is that the universe is getting lumpier and lumpier as time goes forward. And the idea is that the only force of nature that operates over long distances, okay, is gravity. And gravity is a very simple force, and it's easy to calculate what happens when you have two masses separated by some distance, moving at certain velocity, and they have a certain gravitational attraction. You can actually calculate this to very high precision. And so we just, so that's what's happening. So the structure and the distribution of galaxies is getting lumpier because galaxies are falling together because of the action of gravity. So if you yeah, okay. Yeah, I have, what did I say, right? If you turn the movie backwards, then the universe gets more and more uniform as you go back into the past, right? So we are here because lumps have stars have formed, planets have formed, we have formed because of the universe getting gradually more and more lumpy. So that's where the pattern, studying the pattern of the distribution of galaxies in the skies is one of the key measurements of how to quantify that growth, that evolution. And we can look at the clustering of galaxies as a function of time, because if I look at galaxies that are nearby, I'm seeing the galaxies as they were maybe a few million years ago, because it's taken light a few million years to travel from them to us. If I look farther, I'm looking at galaxies that are a billion light years away, and therefore I'm looking at the universe as it was a billion years ago, and so on. So I can keep going back into time and having a direct view of what the universe is doing billions of years in its past. So I can map out how, this is not a theoretical thing, it's actually, I just make the observations, how has this clustering changed with cosmic time? And then when I've finished that set of exercises based on data, I can then ask, is there some sort of framework, or we call it a theoretical model, that I can falsify by saying, does it actually predict this or not? So this is this big enterprise, and it's come into its own since, I would say, the 1990s. We have a word for it, it's cosmology, which is the study of the structure and evolution of the universe at large, and it's almost all to do with just plain gravity. So what you do is you make a model universe, and you say, well, how much, the more mass that's in it, the more gravity, and therefore the bigger the clumping. So the amount of matter is a parameter that we don't know why it's that number, but so we think of it as, we call it a free parameter. We're allowed to adjust the matter, the amount of matter in the universe, so that we get something that looks like the present day structure. And then we have determined a parameter of the model. And then we can go after another parameter, which would be how fast the universe is expanding. By one experiment or another that has more or less power to constrain that parameter, we build up this general framework. And then it either can be shown to be incorrect or incomplete, with new data, or the new data will be consistent with that. So we're not saying we know the answer, we're just saying we are trying to do our best to see whether or not a particular model can be falsified with new measurements, if that makes sense. So the way this works is what you need is okay, so there are many different types of cosmological investigations that include space experiments, they include radio telescopes on the ground, they include all kinds of things. And my particular field is what you might call traditional optical astronomy, which means a real telescope on the ground, okay? With people, the telescopes are on mountaintops, and you go to the mountaintop and you use an instrument. In my case, it's a giant camera, and it produces the map of the galaxies. And of course, there are lots of intermediate steps to go from raw data to a sensible map that you can use for, you can trust for the statistics that you derive from the clustering of galaxies. And this involves, my particular project, the Dark Energy Survey, involves 25 institutions in 7 countries, and there are about 400 people working on it. So it's this an incredibly complicated process of doing the data analysis and validating that we actually have correctly interpreted what we claim to be finding. So it's a very slow process. Right now we've finished, actually as of last year, we finished the collection of data in Chile, and that was after 6 years. I was finishing the 6th year of the season of mapping the sky in the southern hemisphere. And right now we have not yet finished the analysis of the first 3 years of data. Okay, so that should be happening in the next few months. But so that just it is not a demonstration of how lazy we are. It's a demonstration of that it just plain hard. And we just have to look at everything and try to. There are puzzles that arise. Let's see. We have a catalog of almost 700 million galaxies, and a catalog means a set of positions on the sky, how bright they are, and different filters, and how big they are, and sort of structures, what shapes they are. That's important. So you can imagine each galaxy having, let's say, 20 numbers or 30 numbers associated with it. So that's a catalog. With 700 million things, you can get extremely precise measurements of statistical properties with such a huge sample. Okay, so that means that your understanding of the systematic errors, like suppose your measurement of the brightness was a little bit wrong, right? Because of who knows what reason, all kinds of reasons. Or maybe the shapes of the galaxies are just a tiny bit wrong because the optics of the telescope were a little bit out of adjustment, and all of the things you'd done to calibrate that out were not actually totally successful. So the shapes are a tiny bit wrong, okay? So the better your statistics, the harder you have to work to get rid of all those gremlins, all those what we call systematic errors. And that's why it's just getting increasingly hard, because we're getting so good at this that it's getting harder and harder. That's I guess what I'm trying to say. Traditionally, the National Science Foundation and NASA have been the federal agencies who support astronomy, the astrophysical research. Relatively recently, and in fact, I had something to do with this. The Department of Energy has started to fund what we would call astrophysics, but they don't want to just be yet another source of funds for the same people, the same groups of people. So they sort of carved out cosmology as their bailiwick. So they will fund projects in cosmology, but not in, let's say, looking for planets around other stars, which is considered to be, that's NSF or NASA. So cosmology means, or they would call it fundamental physics, so studying dark matter or dark energy, which I will explain, or any of this kind of stuff, sort of anything to do with the origin and evolution of the universe, that's something the Department of Energy will fund. And so by calling this thing the Dark Energy Survey, we made that point that this is, okay, so the dark energy, so with this 700 million galaxies, you can do an awful lot of science, all kinds of astrophysics. And we're finding asteroids that are, in crazy orbits. Which is not something the DOE wants to fund, but we're doing it anyway. But most of what we're doing is cosmology, so it's not misleading. So one of the other parameters, so I mentioned two parameters. The amount of matter in the universe is something we can adjust in our models and compare it with data. The expansion rate, how fast the universe is expanding. And then is another parameter. And the third parameter is whether the rate of expansion has changed with time. Okay, so it's like the curvature of the, well, never mind that. Anyway, it's the change of the expansion rate, and it turns out the universe is expanding, and that the rate of expansion is getting faster with time. So in other words, the expansion is accelerating, and that agent, whatever that is called dark energy, and that's just a name. There's no theoretical framework that is particularly compelling. It's sort of like it's a parameter, right? So in other words, it's a very unnatural thing. It didn't happen that this is very empirical science right now, right? Because we don't understand dark energy. We don't know where it comes from. It doesn't come out of physics in any sort of natural way. So at the present time, we're just trying to characterize, how much dark energy is there, and does that change with time, right? So does the rate of acceleration change? And the interesting thing is that we have this general structure that we call the Big Bang theory, and it very naturally accommodates the existence of dark matter and the existence of dark energy. It doesn't change the framework at all, and that's kind of, to me, it's a remarkable thing that this framework is that robust. It can just, okay, we can throw that in too. That's natural. It's not an unnatural thing to put in dark matter and dark energy. But that doesn't mean we haven't a physical understanding. Dark matter pulls things together. Dark matter is called dark because we know very little about it, but one of the things we know about it is it does not interact with electromagnetic radiation. So light does not come out of it. Hence, dark is a very we see what we see, right? We don't see anything from it other than its gravitational influence. So if you take the four fundamental forces in physics, right, then gravity is the weakest one on small scales, and it's the only one which has an that could realistically have an influence over large scales. But now we're talking about dark energy, which is also pervasive. But we're not counting it as one of the four fundamental forces of nature. It acts more like a pressure than like. So on these cosmological models, we need gravity and we need dark energy. I'm trying to sort of layer on one thing on top of another to try to make there is this other thing which I haven't mentioned yet, which is the acceleration at the very beginning, so which we call the Epoch of Inflation, where the expansion rate accelerated very, very rapidly and smoothed out the kinks, basically. So then the universe became essentially completely uniform and then coasted, and now we have another epoch of acceleration. So I would say that if you asked a very simple question like, why do we have two epochs in the universe which have acceleration, that we just don't know the answer. Yeah, but both of those are first of all, I should say that this Epoch of Inflation does not have nearly the strength of empirical evidence for it. It has a number of reasonably compelling arguments that this is a completely that if you didn't have that early Epoch of Inflation, you have lots of other things that needs to be explained. So this idea comes up with helps us understand things. So if you just have a timeline for the universe, right? So I'm talking about 10 to the minus 32 seconds after the Big Bang. That's the Epoch of Inflation. Yeah, and then,
So that's your question.
this sounds ridiculous, doesn't it? Yeah. So let me give you just to give you a little bit of an insight into why we can speak with some confidence about things that sound totally ridiculous, like 10 to the minus 32nd seconds. So let me say a few other things about what we know that I think are quite solid. So one of the things that we see in as an observational astrophysicist, if I point a microwave antenna at the sky, I see radiation that's coming from all directions. And this is what we call the cosmic microwave background radiation. So it's at 2.75 degrees Kelvin, and it is the relic energy or thermal radiation from the Big Bang, ultimately from the Big Bang. So it's like looking through a completely transparent space up to the point where you see things are opaque. So from the point of view of these light rays, these photons, they originated at what we call the surface of last scattering. Let me try another analogy. So imagine you have a cloud, right? Or a fog bank, right? So it's transparent between you and the edge of this fog bank, and then there's the fog bank, and you can't see into it. Okay, that's just like that. The analogy would be better if the fog bank is glowing, right? So if it's glowing, the light is coming to you from the fog bank. Okay. So we can see up to the fog bank from this globe. Fog bank is 13.7 billion light years away, and if you think of it in the other, there's this timeline. Originates from 380,000 years after the Big Bang. So at that time, the temperature of the fog was 3,000 degrees Kelvin, and now we observe it as 3 degrees Kelvin. And it's only because so there's this as I suggested, a very robust picture of how this radiation gets made and when it was made, right? So we can go back to 380,000 years after the Big Bang, but we can actually go farther back because one of the other sort of arrows in the quiver is the measurement of the abundances, the light elements. So what are the light elements? They're hydrogen, there's helium, there's 2 isotopes of helium, there's lithium, there's deuterium, there's boron, these things, and they have various isotopes. So some of these things, the heavier elements like carbon, nitrogen, oxygen, and everything else are understood to have been created from fusion reactions in the cores of stars like the sun. So the sun is creating helium out of hydrogen now and is creating, will at some point create some carbon and oxygen. All right, so what you do is you study how much stuff there is, how much deuterium there is in the universe, how much hydrogen there is in the universe, and you ask where did the stuff come from? And it turns out that despite the fact that stars are making helium all over the place, that there's just too much helium in the universe to have ever been made by stars by a very large factor, like a factor of 10. Whereas the Big Bang is a perfect place to make helium. So if you go back farther, in other words, if you trust this idea that the space is expanding and that things are getting less dense with time and colder with time because of thermodynamics, everything is cooling down, is expanding. So if I run that backwards, everything should get really dense in the past, really hot in the past. And at some point, when you have a dense and hot plasma, you start to have nuclear fusion reactions. And that's where the helium comes from. And so the helium abundance now is a direct evidence for the existence of nuclear fusion reactions. This is an epoch in the universe that's about 1 to 3 minutes after the Big Bang. And the reason for that, so after a few minutes, the temperature is falling incredibly rapidly. The density is going down very rapidly. And at some point, it just shuts off. And then the neutrons, any free neutrons that are around, will spontaneously decay into protons and electrons. So that's a process that takes about 10 minutes. The half-life of the free neutron is about 10 minutes. So this is connecting sort of fundamental physics, nuclear physics, stuff that we can look at in our laboratories, on terrestrial laboratories, with these this amazing idea that we have an expanding universe. So it's really, really fun. Yeah, so speaking of fun, it's almost like being around, when Galileo was, when Newton and Galileo and those guys were coming up with the concept of forces and, gravity. And it's like that. It's like we have this new thing, the dark energy, and it's a great time to be with. Yeah, so if you go back into time, the effect of the dark energy, it becomes less and less, and the effect of the matter becomes greater and greater, proportionally speaking. So shortly after the Big Bang, the dark energy had no effect at all, and now it's dominant. So dark energy is more important than the matter in terms of the evolution of the structure. The idea here, when I talk about the expansion of the universe and so forth, and when any of my colleagues do, here's how we're thinking about it. So you take some sort of small cube of stuff in the universe, and it's populated by stars and galaxies and planets and whatever, spaceships. And if it's a small cube, you wouldn't think of it as a representative cube, right? It's just whatever you point it down on. But if you make this cube big enough, and it's got enough sampling of everything, it's a little bit like thinking about, how would you do demographics across the United States. You have to have a big enough sample. It's got to sample everything. But at some point, you've got the entire United States in your box. So by definition, you've sampled. At some point, you have a cube of the universe, which is representative of the universe. And what we imagine then is that if you're in this cube, it's by definition like any other cube in the universe. And so there's no, it would be artificial to imagine that there's some cube that has different properties from yours, like it's at the edge. So we don't need an edge, right? To have an edge complicates things, and it makes you have to put more parameters in, which you don't need because there's no evidence for an edge. So why would you want to complicate your picture without any observation? But I can have each one of these cubes is sitting next to all of its neighbor cubes, and everything is expanding all together. So it may be unfortunate. The word Big Bang, suggests an explosion. Right, an explosion is at a point, and you have shrapnel coming out from that point, and so that's sort of what is in your head, and that may be kind of an unfortunate term, because that's not the picture. It's not that there was a space and then there's something happened at a particular point in space. This is where the expansion happened everywhere all at the same time. Yeah, and so there's no edge. Sorry about that. But and there's no center either. The idea is that nobody's special, and so if you had a center, there'd be something special. Therefore, you can't have a center. Okay. So our microwave telescope. So if the microwave background was totally uniform, then we wouldn't bother with building ever more precise and sensitive instruments to measure it, because there's only one number, which is the temperature. That's it. But in fact, there is structure in the microwave background, and it's at temperature variations from this patch of the sky to that patch of the sky about 1 part in 100,000. So it's a very tiny effect. And that lumpiness that existed 380,000 years after the Big Bang is what evolved to become the galaxies that we see now. And so that is actually the heart of this this field, which is to trace the evolution of the tiny little fluctuations way back in the day to the big fluctations that we see now. And the ripples, there are ripples. So you can actually see, but in a representation of the statistics of the fluctuations that we call a power spectrum, you see spikes that are particular length scales that are favored and others that are not favored. And so there are actually ripples in this. And of course, we get a huge amount of information out of that. So there are opposing things, right? So on the one hand, gravity is trying to pull things together. And on the other hand, the expansion of the universe is pushing things apart. So what you actually see when you, let's say, run a computer simulation of how these two things interact together, how these two things work together, is that if you have matter in a sufficiently small region of space already, then the gravity will win, okay? And so you get clusters of galaxies, right? But then if they're too far apart, the expansion wins. And so what you get is the smaller clusters get more clustered, and they're not affected by the expansion of the universe. But the clusters get farther apart. Makes the expansion faster, and so by putting dark energy into the model, you shut down this clustering faster. That's how it works. And so essentially by measuring the clustering, we're measuring the dark energy because we're, the less clustering on big scales there is, the more dark energy. The idea that there's this new sort of anti-gravity, if you want to call it that, this thing that's pushing things apart, that was not part of any theory, is so radical that you might want to think, is there some other, idea that we could use that is not as radical as that? And one idea is that Einstein's theory of general relativity is not the correct theory for gravity on these very large scales. And so whether or not that's more or less radical is a matter of personal taste, right? But the fact is we have tested Einstein's theory to some unbelievable precision on small scales within the solar system, and on reasonably good scales on reasonably good precision on bigger scales, but we don't have measurements on these very large scales. And so it's possible that we should be thinking about modifying gravity. That's the term that we use. And so actually these experiments that I've been talking about have the potential to do that, to test whether or not the things would go in the direction of modifying gravity or going in the direction of dark energy.